You have probably already seen a chart like this with direct numerical simulation, large eddy simulation, and Durance simulations put into a triangle like this, with DNS being the most costly, but also the one with the most resolved physics. What is often left out is the question of how costly. In this video, we're going to investigate why DNS is so expensive. Hi and welcome to this new video. We want to investigate why computations of turbulence are so expensive, and expensive refers to the computational cost, or in other words, how kind of a beefy machine you need in order to solve the simulations. And spoiler alert, what we are going to come up with is that the cost of direct numerical simulations is going to be roughly the Reynolds number of our flow cubed, and then we will look at some examples what this means for realistic engineering applications, also in comparison with the world's most powerful supercomputers. But let's start from the beginning. What are we talking about? So we are talking about turbulence, a super interesting phenomenon in fluid mechanics, and you've probably already seen that. It's these eddies which are created in fluids at certain conditions, and those almost appear to be random and appear in all kind of sizes and timescales. What is particularly intriguing and also difficult about turbulence is that it is a chaotic phenomenon. This is a mathematical concept, which means that it is highly sensitive to initial conditions. So if we start off our simulation slightly differently, we will end up with a different turbulent state in the long term. But the more problematic is, the second point, is that it lives in multiple scales. And you can think of scales as some sort of orders of magnitude. So here I just painted a couple of eddies, but once you have a quite turbulent flow, those eddies appear to be super large and also super small. And they appear also over different ranges of time scales. So there are eddies which appear over a couple of seconds, but also some over just microseconds. And the problem here is that the small scales, so in other words, the small eddies which persist over smaller timescales, they affect the larger scales. And the problem there is if you then want to compute your fluid flow, which is turbulent, and then you don't resolve the smallest scales, you might end up with an incorrect solution. So it is highly important that we account for the effect of the smaller scales. And what is interesting is that most engineering applications are turbulent. So most engineering applications are turbulent or consist of turbulent flow, and the effects of turbulence are extremely relevant. Before we will start talking about the computation of turbulence, let us first consider the question, when is a flow turbulent? Because a flow does not necessarily have to be turbulent. I mean, I said most engineering applications are turbulent, but we don't always have turbulence in our simulation. For this, let us look at the macroscopic definition of fluid flow, the incompressible Navier-Stokes equations. Here I want to look in a particular form of them, which is the dimensionless form. So we're not considering units like meter or seconds. So this is just a general mathematical effect. And then our equations consist of the temporal derivative of a velocity quantity here, plus the convection term, which is u dot product nabla times u. And on the right-hand side, we're getting the negative pressure gradient plus 1 over Re times the Laplace operator, nabla squared basically, times the velocity again. And then we have a constraint or a second equation, which is that the divergence of our velocity field has to be 0, which is the incompressibility condition. And this quantity, 1 over Re, is quite important here. I would even argue that it is one of the most important dimensionless numbers in CFD. It's the Reynolds numbers. So the most important dimensionless number in CFD. So dimensionless number in CFD. And that is the Reynolds number. And dimensionless means that it's kind of independent of what kind of geometries we are looking at. That's because the overall flow characteristic between flows which are at identical Reynolds numbers are comparable. And the Reynolds number is roughly defined as the ratio between the convective transport and the diffusive transport in our equations. So the diffusive transport is in the denominator. And based on that, we can of course derive that if we have a large Reynolds number, then we have a convective dominated flow. So convection dominated flow. So because then we have a large numerator, whereas if we have a small Reynolds number, we have a diffusion dominated flow. And you have to think of this as roughly, not that there's like this hard cut from a certain point where it's then convection dominated and diffusion dominated. Just think of it like in superrelative terms or orders of magnitude. And if we look at the incompressible Navier-Stokes equation, we can also see that. So if the Reynolds number is getting super large, then we are dividing 1 by something that is super large, which is approximating 0 then, and then the effect of the Laplace operator, which in essence is a diffusion, will be going to 0, whereas the effect of the convection, which is this quantity here, will become dominant. You can for this ignore the inertia term and the pressure gradient. Whereas on the other hand, of course, if the Reynolds number is getting towards 0, then we have the division here, 1 divided by a small quantity, even one that is getting below 1 and approaching 0 there, then we are getting a larger and larger number, and then we have a larger contribution from the diffusion term, whereas the convection term is getting smaller. And you can even put this into the extremes and say that if the Reynolds number goes to infinity, then we are getting the Euler equations, which in that case don't have diffusion at all. And if the Reynolds number goes to 0, then we are getting the Stokes equations, which don't have convection at all. And why am I bringing this up? That is because in our Navier-Stokes equation, we see that these partial differential equations are nonlinear. And the nonlinear contribution is in the convection term. So this is the nonlinear contribution. And to some extent, it is believed that these nonlinear contribution can explain the turbulence that we see in real life to a high degree. So of course then, if our Reynolds number is getting large and the diffusion influence is getting small, the nonlinear influence into our equations is getting higher, and therefore we see stronger turbulence in our flow. So we can then add here that for large Reynolds numbers, we have a convection dominated flow, and this is then problematic in terms of direct numerical simulation, because the convection is associated with the nonlinearity, and therefore also the turbulence. And therefore we say for larger Reynolds numbers, we have a more turbulent flow. But that does not fully answer the question of when a flow becomes turbulent, and that greatly depends on the geometry or the investigated effect one is looking at. For example, we can look at pipe flow, which is probably one of the most simple cases there. And there the literature kind of says that for Reynolds numbers greater than 2300, we have a transition to turbulence. So in other words, when we are smaller than 2300 in our Reynolds number, we still have a laminar flow, so which is kind of the opposite of a turbulent flow. And then we say that if the Reynolds number is greater than 4000, we have a fully turbulent flow. And then after this 4000, we associate the intensity of the turbulence, or also the ranges of scales in our turbulence, with the Reynolds number. Well, now we looked at this kind of like this ratio between convective and diffusive transport, but how would you compute the Reynolds number, for instance, with some real data? So how to compute the Reynolds number. And here we look at the some of more detailed definition of the Reynolds number, which is that it is given as the ratio, and in the numerator we have a characteristic length, so a characteristic length multiplied with a characteristic velocity. I will come back in a second what it means to be characteristic, and then we divide by the viscosity. And based on that, we can say that the Reynolds number gets higher. So let's say, i.e., we have a higher Reynolds number if, first point that can happen is our geometry is larger. So the geometry is large. Or second point, this is this one here, our flow moves fast. So the fluid moves fast. And the last point is that we have a high Reynolds number if the fluid is rather inviscid. So the fluid is rather inviscid. So in other words, it is not having viscous effects or only in small influences. And to answer the question what is meant by a characteristic length and a characteristic velocity, that's of course a little bit fishy and depends on the scenario. But for instance, if you were to simulate the flow over an airplane wing, then you would, for instance, consider the chord length of the airplane wing as the characteristic length, and you would consider the fluid velocity at the inflow of your computational domain as the characteristic velocity. But in the end, it does not greatly matter, because even if you would select half of the chord length, this would not greatly alter the order of magnitude for the Reynolds number. So for instance, then one would redefine the point where transition to turbulence happens. And in the estimates we're going to do, it is more interesting whether our Reynolds number is 10,000 or a million, and not the difference between 10,000 and 25,000. So kind of think of this roughly in that sense. And I want to highlight one point here, especially with respect to engineering simulations, is that those typically only encounter two kinds of fluids. So let's say typical engineering CFD maybe considers only two fluids, or the typical engineering CFD fluids are air and water. And these two have a kinematic viscosity of, so new air is at standard conditions going to be 1.46 times 10 to the minus 5 meters squared per second, and the kinematic viscosity of water under standard conditions is 1.14 times 10 to the minus 6 meters squared per second. And the point I want to highlight here is these 10 to the minus 5 and 10 to the minus 6. And since these kinematic viscosities are in the denominator of our Reynolds number definition, those mean that even if we have a characteristic length and a characteristic velocity of only 1 and 1 meters per second, so let's think of unit for the second here, then we will still have, or we already have, a Reynolds number of 10 to the 5, which is 100,000, and 10 to the 6, which is a million. So let me note that down. So even if our geometry is only 1 meters in length and the fluid flows at 1 meters per second, we already have a Reynolds number of greater than 100,000. So we already have a Reynolds number greater than 10 to the 5. And now consider the following, that typical airplanes, so commercial airplanes, have cruising speeds of velocities, so they have velocities of greater than 100 meters per second, and this would just add 2 orders of magnitude additionally to it. And maybe if we roughly also think of geometry in that sense, we can maybe approximately say that for aerospace, we have Reynolds numbers which are roughly 10 to the 8, which would be 100 million, so crazily high. But that's all good so far. Now we know how the Reynolds numbers in engineering applications are. And of course, arguably, these are high numbers, but this does not necessarily mean that we also need large computational amounts. So now let's look at how the Reynolds numbers affect the scale of turbulence. So let me phrase the question, but how does the Reynolds number affect the scales of turbulence? And here we are resorting to some really early work on turbulence, which is the Kolmogorov scales. And those can be simplified in the following way, so that we have a length scale. So in other words, the size of the smallest eddy. We have a time scale. So in other words, over which range of time do the smallest eddies persist. And we have a velocity scale, which means how fast are these eddies moving or rotating. And here we can approximately say that the length scale, also called eta, is a quantity which is of the order of the Reynolds number to the minus 3/4. The time scale, sometimes called tau underscore eta, is of the order of the Reynolds number to minus 1/2. And the velocity scale, u index eta, is of the order of the Reynolds number minus 1/4. And if you want more details on why these numbers pop up, I would recommend you to look at the book of Pope, which is a classical reference there, which is just titled Turbulent Flows. So it's now interesting to see how large and how fast and so on and so forth these smallest eddies, these smallest scales are moving. How does this affect our computation? And for this, think of the fact that if you use a discretization that is larger than these scales, you don't resolve these scales. So let me note that down. If you use a discretization that is larger than these scales, you do not resolve them. So in other words, you do not account for their effect then. And that is again problematic, as said earlier, because the small scales influence the large scale. So you can also think of the length scale as your desired spatial discretization and of the time scale as your desired temporal discretization. So for instance, if you look in 3 dimensions, because turbulence is a 3-dimensional phenomenon, and your computational domain is, let's say, this box here, and then you discretize this box here in that direction in this particular way, then this distance here between the 2 discretization points, which then make up these small cubes in there, I think you might get the point, hopefully, this delta x here has to be smaller than the eta, and the eta was of the order of Reynolds number to the minus 3/4. And if we look at our aerospace example with the Reynolds number of 8, that means that your spatial discretization has to be approximately 10 to the minus 6. And if you are thinking in units of meters, for instance, this would mean that your spatial discretization has to be in the orders of micrometers. And then for the time, so if you have a temporal axis and you start at 0 and then you have your time steps here, in order to transiently evolve your simulation, you make a step from one step to the next one. Then in between them, you have a delta t, and this delta t then has to be smaller than the timescale length, and the timescale length was given as Reynolds number to the minus 1/2. And again, for our aerospace example, that would mean that delta t has to be approximately 10 to the minus 4. So if we are thinking in seconds, this would be in the hundreds of microseconds. And I hope this thought is kind of moving us closer towards our estimate on the computational cost of turbulence. So let me phrase the next question of what does that mean for the computational cost, for the computational cost. And for this, we have to be aware that As said, we are in 3 dimensions. We have to discretize our, in that case, cube domain. So let's use that example of a cube domain. And then we can say that the number of degrees of freedom per axis, so degrees of freedom per axis, let's take for instance the x-axis here, will then be 1 over the discretization length. And the discretization length was limited by the scales of our turbulent. And so this one will be effectively in the order of Reynolds number to the 3/4. And then the important point is we are in 3 dimensions. So in 3D, we will have that the total number of discretization points, or the total number of degrees of freedoms, let's call this capital N, is going to be nx cubed. And this will then therefore be of the order of the Reynolds number of 9/4. And then, as said, we also do our time steps. And this is the next question, how many time steps do we need? So the number of time steps, and let's call this capital N. And here we are usually interested in accounting for a full cycle in turbulence, which would be going through all the scales that appear in those turbulent flows. And therefore we have to go over a unit step in time, or something that is of the order of that, maybe 20 units in time or 40 units in time, but something that is uncoupled from the actual turbulence scale, or maybe 20 or 30 or 40 units of time. But let's, for the simplicity, let's just use 1 unit of time. So 1 over the tau eta. And this will therefore be in the order of the Reynolds number to the 1/2. So now we know how many degrees of freedoms we have. That's of the order of Reynolds number 9/4. And we know how many time steps we have to do. By the way, these degrees of freedom, this is also the memory that you need. So because you need to store the value of each velocity component at the degrees of freedom plus some overhead, but so it will be in that order. But now in order to get the computational cost, we need to know how high is the cost per time step. So next question, how high is the cost, and again the computational cost, per time step? And for this, we have to look at how we usually evolve in time. And commonly we have 2 approaches there. We can either go explicitly, so we can have an explicit time stepping, or we can go implicitly with an implicit time stepping. Usually if we do it implicitly, we either have no restriction on a time step length, or we just have a minor restriction. Commonly, if you do explicit computations, then the cost per time step is of the order of the number of degrees of freedom, because you have to update each number of degrees of freedom. So this will be linearly in the number of degrees of freedom. And for the implicit, that kind of depends, because usually when we have an implicit, we are solving a linear system. So solving a linear system, or sometimes even we have to solve a nonlinear system, but that is still in the order of solving linear systems. And there we have different approaches. In the most desirable case, we have an order of n complexity, which can be achieved with multi-grid algorithm. Although this takes a lot of tuning in order to get that complexity, we can have a complexity of n log n for fast Fourier transformation based spectral methods. And we have complexity of k times n when we use Krylov solvers, so for instance, conjugate gradient, GMRES, and we get a complexity of n cubed if we use LU or QR decomposition. But here, of course, we could say, well, hypothetically, we might have a multi-grid procedure, but let's just use the explicit time step for now. Just say, well, this is desirable because then we have our linear scaling in the cost per time step. But before we can assume that, we have to ask ourselves, are we stable? So let me put that here and say, are we stable? And stable in a sense of, do we have a stable numerical simulation? And the common measure here is that we are looking at the CFL number. So the CFL number, and this one is defined as the time step length multiplied with the largest velocity divided by the largest discretization in our domain, and this one has to be smaller than a certain constant, and common values are 0.5, 0.7. So we can just say this is in the order of 1, so this is a constant quantity. So in other words, the CFL number is independent on how turbulent our flow is. And then we can rearrange that in order to get that our time step length has to be smaller than delta x divided by u times this O of 1 CFL number. So let's just leave that out and say this is in the orders that we define for our delta x and delta u. So we have order of Reynolds number to the minus 3/4. That was the length scale in our turbulence, divided by the order of Reynolds number to the minus 1/4, which was the velocity scale that we had. These are the usual velocities we are experiencing in our simulation. And then let's just apply the rules here and say that this is in the order of Reynolds number to the minus 3/4 plus 1/4, and this then, under simplification, yields Reynolds number to the minus 1/2. If you recall, this is actually what we also got in our scales. So let me go all the way up here and see that the time scale is already in the order of Reynolds number to the minus 1/2. And now we figured out that according to the other scales, we need a time step length, which is also in that order. And this then means that we are lucky and we can use explicit time stepping schemes in almost all kind of turbulence scenarios, because the time step length we need in order to be stable is exactly the time step length that we also need in order to resolve all scales. And that's quite an important finding. Therefore, let me note that down and say, maybe make a happy smiley here. So, and say that's exactly our time scale of turbulence. And in other words, because that's such an important remark here, so the direct numerical simulation we want to do allows for explicit time stepping methods, and that is because the step length required to be numerically stable, so numerically stable, is also the step length required to capture all scales. And that's great. So now we have the cost per time step and we have the number of time steps. So just multiply the two and we get the total cost. So let me have the last question. What is the total cost? And here we just say that the total cost is the cost per time step multiplied with the number of time steps. And we say that in our explicit time stepping scheme, the cost per time step is of the order of the degrees of freedom, because we have this linear updating, multiplied with the number of time steps, which was given according to the Reynolds number to the 1/2. And then let's just replace what was the order of the number of degrees of freedom. This was nothing else than in the order of the Reynolds number 9/4 multiplied by the order of the Reynolds number in 1/2. And let's just add these two exponents together, and then we're getting this is in the order of the Reynolds number 11/4. And we're just missing 1 in order to have a 12 in the numerator. So we can approximately say this is of the order of Reynolds number to the 12/4, which is in the order of the Reynolds number to the 3. So the Reynolds number cubed. And that is this really important finding, and you see that quite often in some papers that are concerned with turbulence, that the computational cost of a full turbulent flow is in the order of Reynolds number cubed. And here remind yourself again, it is not really important whether you're now looking at Reynolds numbers of 10,000 or 15,000. So it is rather the order of magnitude. So of course, it then also depends on some clever implementation, but in the end, that kind of gives us a rough estimate or a minimum bound on the computation that we might be expecting. And let's look again at the Aerospace example. So Aerospace example, where we had a Reynolds number of 10 to the 8. And this then means we have in the order of Reynolds number to the 24 necessary computations. And what is a measure of computation, and a typical measure here is the floating point operations. So the number of computations that we have to do, additions, multiplications, subtractions, and so on. But what does it mean like in practical terms? And for this, I have this table here that is taken from the Top 500 website. There's a website listing the fastest supercomputers on the world. And here we have the top 3. We have a Japanese computer and 2 computers from the United States. And what we are interested in are these 2 columns here. So these are 2 different measures of their floating point operations. So let's just for the simplicity take the higher one here. And they are measured in teraflop per second. And teraflop is 10 to the 15. So it has 500 times 10 to the 15. So 500 times 10 to the 15 floating point operations per second. And remember, we have here for our aerospace application, we have 2 to the 24 floating point operations necessary. And maybe just for the simplicity, let's assume an exascale computer. So let's assume an exascale computer. This one would be having 10 to the 18 floating point operations per second. It's expected to be seen in the next 2 years or so. And if we then make a number crunching, this then means we need 10 to the 6 seconds. And this 10 to the 6 seconds are approximately 1 month. So a million seconds is approximately a month. And now you might say, well, it's great. So we just need 1 month on the fastest supercomputer. And I claimed that you can't solve DNS. Well, that's true. You could do that, given that you implement it in a really efficient way. But the interesting aspect of engineering simulations is that you are not interested in just one simulation, but usually you're interested in more than one because you want to do optimization or design exploration. So let me note that down. This is for one computation, but commonly one needs greater than 100, maybe 1,000 computations or simulations for design, optimization, and exploration, or to create surrogate models, etc. And then if you were to do like these 1,000s, you need 1,000 months, and well, that makes it kind of infeasible. And now you could argue, well, we can maybe just wait for faster supercomputers. So there is still Moore's law. So just let me highlight that one here. So Moore's law, which goes back to the Intel founder Moore, which said that the roughly speaking, that the computational power doubles every 18 months. So doubles or doubled power, or not power, maybe power is the wrong word, let's say strength of the computer every 18 months. Although over the last years, this has kind of like a little bit flattened, so it's not that strong anymore. But even then, you can still make some computations and see that it's not really reasonable or not something that we can expect in the future. And one more aspect that I want to highlight here is that you can also look at the power consumption of these computers. So they have a power consumption, so the fastest one, the Japanese here, of 30 kilowatts. So that's quite a lot of energy. If you imagine that an average household takes around 1,000 to 2,000 kilowatt hours per year in energy, you would actually need that amount of energy for quite a long period of time in order to perform all these computations. And then, of course, you have to outweigh what are the benefits of the simulations. Do you really need direct numerical simulation? Are you just curious? So it's super interesting to see here. And here we were just looking at an aerospace example, and the things are getting worse if you are, for instance, looking at Mach jets which are flying at velocities greater than Mach 1, Mach 2, and so on, or also astrophysical examples. So let me note that down, that astrophysics usually has Reynolds numbers that are 10 to the 12, so 4 orders of magnitude larger than aerospace. And then if you want to, for instance, simulate the collision of galaxies or something in that regard, you easily run out of the resources we are expecting to have in the next 100 years. at least for classical computing. And I hope this was an interesting insight with using these Kolmogorov scales. And maybe the really important finding you should take away here is that for direct numerical simulations, that this cost of this computation scales with the Reynolds number cubed. A big thanks to all the Patreons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please hit the like button and subscribe to the channel. There are more similar videos to that on the channel. Here you now see similar videos, and I hope to see you in the next one.